Hello. So we are gathered here today to mark the ICTS Foundation Day, but we do so under the shadow of the passing away of Dr. Manmohan Singh, one of the greatest sons of Bharat, as our Honorable President of India put it. Dr. Singh exemplified, I think, in his person the best of when academia and public service come together. I think I had circulated a note today, many of you might have seen, from Professor Shashidhara, which outlined his impact on Indian science. In fact, at ICTS as well, it was during his tenure as the minister in charge of the DAE that the cost revision and the final campus or construction budget of the ICTS was approved. So in some sense, we are, I think, by gathering here in these rooms and facilities, I think we express our thanks to him. So while, of course, we will have to cancel the celebratory events of the evening, but I felt it would be a fitting tribute to his memory to continue with the ICTS Foundation Day lecture, since academics was very close to his heart. So it's also my privilege to welcome today as special guests of honor to this lecture, Shri Tatineni Prem Kumar and Srimati Sujata Kumar. Shri Prem Kumar and Srimati Sujata Kumar have been very generous philanthropists who have supported the humanities as well as sciences. They have set up the Muturi Satyanarayana Center for Advanced Studies at Kriya University in the humanities and in the sciences at the Chennai Mathematics Institute. So it is a particular pleasure for me to welcome them here and also to announce that they have agreed to support at ICTS very generously and establish the Tatineni Prem Kumar and Sujata Kumar Travel Grant Endowment at ICTS, which will facilitate the ICTS students and postdocs to travel to international meetings and collaborative workshops. So I particularly want to thank them on behalf of the ICTS community for their establishing this generous travel grant, and which will, I think, make an impact in many of your lives and careers and give you the exposure and the ability to talk about your work in a very broad international forum. So I would, before we start the lecture, I would just ask you to say, maybe you don't, I know you are a little embarrassed, but perhaps just a few words to.
Both in humanities and mathematics. We have set up a center at Kriya University, Muturu Satyanarayana Center for Advanced Studies in Humanities and Social Sciences, and Chennai Mathematical Institute for postdoctoral students and also for travel grants. And when Dr. Wadia approached me, I said, okay, we'll do something for ICTS also. And Dr. Gopkumar suggested that the best way to do is give grants for the travel for the postdocs and the research scholars who require the exposure to attend international conferences and seminars. With that idea, we have given the grant here. I created an endowment. I think it will support most of the postdocs and research scholars. Thank you very much.
Thank you, Shri Prem Kumar, for the trust you have reposed in us. And I can assure you the students at ICTS are doing wonderful work, and this will enable, I think, give them the chance to sort of really to take it to another level and open up many more opportunities to them. So let me now proceed to the main event of the evening, the lecture by Professor Deepak Dhar. So as you know, in our Foundation Day lecture, we always invite an eminent scientist to tell us about something interesting, something maybe we don't hear too often. In that tradition, we have, of course, today our very own Professor Deepak Dhar to tell us about some things in game theory. And as you might have seen, a very fascinating abstract and title of his talk. So just a few words of introduction, since it's customary. Professor Deepak Dhar is a theoretical physicist who is very well known for his contributions to statistical physics and stochastic processes. He was born in Pratapgarh in 1951, and after his bachelor's at University of Allahabad and the master's in IIT Kanpur, did his Ph.D. at Caltech. Since 1978, Professor Deepak Dhar was at the Tata Institute of Fundamental Research in Mumbai, and from where he retired as a distinguished professor in 2016. Subsequently, he was at IISER Pune for some years, and has since April of 2024, he has been the INSA Distinguished Professor at ICTS. Professor Deepak Dhar has made very fundamental contributions to statistical physics, and for this, one of the signal recognitions was the Boltzmann Medal of 2022. I think this is one of the highest honors in the field of statistical physics, and Deepak was the first Indian recipient. He is, in addition, a fellow of all the Indian Science Academies and TWAS. He's recipient of the Bhatnagar Award 1991, the Padma Bhushan in 2023, and the IITK Distinguished Alumnus Award in 2022. So of course, I don't need to belabor the point, but I just want to add that ICTS and in many other institutions in India, the statistical physics, the groups in statistical physics in India owe a lot to Deepak. Professor Abhishek Dhar, who is here, was one of his very early students, and many other centers all around the world, in a sense. Professor Deepak Dhar, together with Professor Mustansir Burma, created a school of statistical physics in India, which I think is a wonderful, great contribution. So with this, let me invite Deepak to deliver his Foundation Day lecture. Thank you.
So thank you very much, Rajesh, for the kind introduction. Let me start by giving my own homage to Dr. Manmohan Singh, who was very supportive of science in his tenure as the Prime Minister. So in talking today, I thought I will discuss something which is more of general interest. So I picked some paradoxes in game theory. Let me say that I don't expect most of you to be experts in game theory. So this is sort of a non-technical talk. But maybe if there is some issues which you feel uncomfortable with, you shouldn't worry. You should take it as an overall view of the subject, and that should be good enough. So let me start. As children, we all enjoyed playing games, and even non-human animals play games. At least I know dogs like to play a lot of games. Some other animals, dolphins and so on. This is known to be an enjoyable activity. Okay. There are many types of games. One can have games of skill like 100-meter dash. So, this is included in Olympic Games. So it is certainly a game. There are games of luck like snakes and ladders. We have all played as children. So in snakes and ladders, it is just you throw some dice, and depending on the outcome of the dice, the pieces move and somebody wins or somebody loses. And if you play against 6-year-old, you will not be at a particular advantage or disadvantage. It just depends on how the game goes. But then there are things called games of strategy, which, the simplest one is, not simplest, but close to simplest is tic-tac-toe, which you can play against children. And, at some age they learn how to play. Before that, they will not be able to play very well. So, of course, this chess is a little bit more complicated than tic-tac-toe, and people haven't understood how to play it very well. For tic-tac-toe, it is known that there is a strategy. If you play first, then you can always win. But for chess, it is not known that there is some good strategy which always makes you, which will ensure that you will win. That is why the game continues to be played. But there is a theorem that either the white can always win or the black can always force a draw. And right now people are not able to decide which one is which. But once they are able to decide, then the chess as a game will be dead. Then there are other games like poker, which are not purely games of strategy. They involve a little bit of luck and a little bit of strategy both. So these are more complicated games. The mathematical theory of games was started by von Neumann and Morgenstern in 1942. And this deals with the last category, games of strategy. Strategy with luck, without luck, game within full information, with incomplete information, whatever. And it lets you find the best decision in a complicated situation. So as a very dumb example, I'm playing poker, I have some hand, all these other people are playing, this guy has raised, now do I fold up or do I raise? That is the decision I have to make. It's based on what cards I have, what other people have. And so this one, or for example, I have a product in the market and I want to introduce a new product in the market, then I have to choose a price. The price is too low, then I will not, sell much. If the price is too high, nobody will, if the price is too low, I will not get a lot of profit. If the price is too high, I will not sell much, which again I will lose. So, what is the best price I can make, or all these kinds of stuff. So it has been applied, the game theory has been applied in many real world situations like markets, war games. It became very fashionable around 1950 or so with some Rand corporation in the US. They were deciding nuclear war, how should you, what kind of strategy you should take, and what if this guy says this, what should be my next move, and so on and so forth. And matchmaking, I have written it like this, but it is, we will get to it later. So let us just go on. So it has been applied to many real world situations, like I want to buy a stock, which stock should I buy, how much should I buy, and that kind of stuff. People try to use game theory in such situations. So in the applications of game theory to real life problems, one has to define the problem precisely. That is if you want to have mathematics help you in finding the solution, you have to express the language, express the problem in a way the mathematicians can understand it, which says that it has to be defined precisely. This is already a problem. So for example, my problem would be that I go to a shop and I want to buy a shirt. So there are shirts, lots of shirts, some have high price, low price, some have nice color, not nice color, good style, bad style. And I have to pick one. So which one shall I pick? That is a typical consumer decision problem which is encountered. And what do? I often, I make a decision. But a mathematician will say that if you have competing criterion, I want the price to be good, I want the style to be good, I want the color to be good, then you cannot optimize the solution with conflicting criteria. So what you got to do in that case is to make a weighted average of all these different qualities, and then you maximize the weighting average. The weight you choose yourself, that's up to you. But it turns out that when I go to the shop, even in my head, I don't have a weight assigned to the price versus the color. And I just choose somehow or the other. And so in many of these problems, the quantity I'm trying to optimize is not precisely defined. Then you cannot apply game theory there. Okay? So I just wrote down shadi.com. Suppose you want to find a mate, life mate. Then you want them to be beautiful, you want them to be intelligent and rich and all these qualities. And these are not always compatible, of course. And you got to make a decision. And I don't know anybody who has a rule which says that 0.3 times the score for beauty plus 0.7 times the score for this. And, they don't have a weighted average of different qualities when you want to decide some very important decision in your life. Okay? So unfortunately, even in such situations, the game theory cannot help you, because the quantity you are trying to optimize, you haven't defined it in a way the mathematicians like. Okay? So the way mathematicians like the game theory, they say that there are some agents. Every agent has some actions he can make, A or B or C, so they have a choice. But the second agent also has choices A, B or C. And depending on the choice of all the different agents, every person gets some result, outcome. The outcome can be happy for A but unhappy for B, and so on and so forth. And it depends on the choices they make. And so they will say that the outcome is specified by a payoff matrix. We will say a little bit about this later. But in the simplest setting in game theory, the payoff matrix is known to all people. Everybody knows what is the game. So if you play this and that guy plays this, this is what he will get, this is what you will get, and so on. Okay? So once you know this, then you have to decide what you should do, which strategy, which option to pick. Every agent has to pick some particular action and then try to optimize his payoff. Okay? So even in cases where the payoff matrix is known, of course, sometimes you don't know it well, but you have to estimate it in some way. It is not easy to choose. I give you a simple example. There is a lottery. The cost is 1,000 rupees. And with 1% probability, you will get 2 lakh rupees. And with 99% probability, you lose, you don't get anything. Okay? So if you calculate the expected payoff, it is 0.1 times 2 lakhs is 2,000 rupees. It is more than the cost of the ticket. So you might think that you should get it. But actually, I know a large number of people who will not take the lottery. Okay? Because most of the time you are going to lose, and losing 1,000 rupees is much worse option for me than, with the small probability of getting 2 lakhs of rupees. So it turns out that expected value of payoff is not what decides what I do. Okay, so this problem, of course, has been understood by psychologists and game theorists as well. So they said that no, it's not the payoff that you optimize the utility of the payoff. So you don't optimize the money, you optimize the utility of the money, and the utility of the money decreases when you have a lot of money. If you are already a crorepati and I give you 1,000 rupees, you are not particularly grateful to me. But if you are only, if you have a few thousand rupees and I give you 1,000, then you are much more happier. So the utility of 1,000 rupees is more when you have less money than otherwise. So what you should optimize is not the value of the money, but the utility of the money. Then in this previous example, so we said that there is a lottery ticket, it has 2 lakh payoff. I will not maximize the expected value of payoff. I'll optimize the expected value of utility of the payoff. So minus 1,000 rupees has some utility and plus 2 lakhs has some utility, but the utility of 2 lakhs is only 3,000 plus 3,000 minus 1,000 is let's say minus 500 or whatever. And maybe it will work, maybe it won't work, depending on the utility you assign. And the utility is assigned by the particular agent. And typically in most games, it's not known to other people. Okay? So I don't know what you will choose because even though when I know the payoff, I will not know what utility you are assigning to the payoff. So this was sort of given in the context of nuclear wars. So you have these two leaders, at that time it was America and Russia, and they are deciding on the outcome. Now one of the options is that there is a big nuclear war and the whole world becomes uninhabitable or some such thing. What is the utility value of this? Minus 1,000, minus 1 lakh. Okay, depending on the answer, if you choose one option, your answer is plus 10. If you choose another one, it is minus 100. But the probability of the second one is low. But is it minus 100 or it is minus 1,000? I don't know. Even if I know the value I assign to this stuff, I don't know the value Mr. Khrushchev is assigning to this stuff. And so that makes the discussion of game theory much more complicated because we don't know what other agents are doing, would like to do. Anyway, then the other thing which game theorists usually do is to start by saying that all agents are rational people and they know other agents are also rational. This is a very technical word, but it means they are not foolish and they are not, if they are going to do something very stupid, like I will do something which actually is harmful to me, then I'm just crazy and I should not be playing the game in the first place or some such thing. So you expect that other business people are trying to do good for themselves. They are not trying to ruin themselves. So that's a basic assumption which goes into this, and that's called rationality. But even this condition is not easy to satisfy. So this also has been discussed in game theory a lot. They call it bounded rationality. So as an example, there is the stock market and there are all these people with a lot of information and data and they are trying to decide where to invest. But most of the people who work in stock market, I think, will not know how to solve a cubic equation. It doesn't seem to bother them much, but a perfectly rational person is expected to be able to know this immediately. No rational person, you give him a cubic equation, he will immediately say this is the root, this is the one I should use. Okay? So this bounded rationality is very hard to satisfy. There are other versions of this, but so this is a technical word, but it explains the general idea quite well, I think. Then there is another thing called trembling hands. So, I'm buying stock and then they say that, okay, you choose this option, sell. But when I hit the key, I hit the wrong key. It happens sometimes, it can happen. So even if you have a desire to make an action, you might make a mistake or you might fumble a little bit. That is called trembling hands. And it is very hard to take care of this in standard game theory. Okay, of course, there are variations. All of these problems have been discussed in game theory. But I'm pointing out the complications involved in all this. And the last one is actually very simple. It says that if you had infinite computing power, then you will be fully rational. And by definition, mathematicians assume people have infinite compute. Given choices, they will be able to tell what to do. But if people had infinite computing power, chess would not be a game people will play. Okay, so you have to take into account the fact that people only have a finite amount of time, a small computing power. Within that time, they have to make a decision. This thing is very hard to put into the game theory discussions. Okay, I actually, even when people say these words, I do not know of too many examples where in the payoff function they put in the time to compute the answer or some such thing. Sometimes it's put in the constraints that you have to decide within a day or some such thing. Okay, anyway. So I thought I will discuss some paradoxes in game theory which are easy to understand. And so let me start with this, the prisoner's dilemma. This is a very famous game which is taught to undergraduates in game theory in the first course on game theory. So, but let me describe it to you. It was described first by Flood and Drescher, and then some the language was changed a little bit by other people later, but let's not worry about that. So the game is defined like this. There are two prisoners, they have done something, and police has caught them. But the police don't have enough evidence to convict them just now. So what the police warden does is that he puts these two people in different cells, and he offers them a plea bargaining. He says that if you confess, and you also say that this other second person also was working with me, then I will give you a lighter sentence, and the second person will get a heavy sentence. Okay? So this is, and this he says to both of them. Okay? But these two people are in separate rooms, they are not allowed to talk to each other. So what should they do? So this is what he says. If he or she confesses and testifies against the other, he'll get an easier deal, and the other will get a stiffer punishment. Okay? So then this is part of the definition of the game. Each prisoner is selfish and only wants to reduce his own sentence. And he knows that the other person is also offered the same deal. And they have to decide one day, next day you have to tell, are you going to do A or B? And this is the payoff matrix. This is the agent A and B. If B stays silent and A stays silent, then A will get both of them are silent, then they don't have enough evidence, they will get 1 year in jail, both of them. If this guy stays silent and this one testifies, then he will get a stiff sentence, 3 years in jail, and this one will 0 years in jail because he has got plea bargained. It's symmetrical. If this guy testifies and this guy doesn't testify, then he will get 3 years in jail and this guy will be 0. If both of them testify, then both of them get 2 years in jail. Okay? So then it's a very simple choice. What should you do? Okay, picture is taken from Wikipedia. And what will rational agents decide? That it's a simplest of these decision problems. So there is a complicated argument that says that the rational thing to do for both prisoners is to testify against the other. So this is what is taught in all game theory courses. And then those students become professors, then they teach their students the same thing. Okay, so let's go through this argument. It's given in this one line here. It says this is the best choice A can make. So suppose I'm trying to decide this. I say, suppose B stays silent, then I will be better off if I testifies, because then I will have -1 versus 0. Suppose B decides to testify, then if I don't do it, then I get -3. If I do it, I get -2. So I'm still better off if I testify. So the answer is both of them should testify. That is the rational thing to do. That is what was said. Okay? But clearly this is not the best choice. If both of them stayed silent, both of them will get -1. So this is the confusion or paradox. Why are you telling me that the rational thing to do is for both of them to testify? Okay. So this point, of course, is well realized. This was the point of the game. But the argument given seems quite convincing. How can both rational agents decide that it is better for both to testify? That is the paradox. And the resolution of the paradox lies in going beyond each agent optimizing, assuming that the other people have made their choices. So the way I presented the argument, it said that B has made a choice, he's either this or this, then I'm choosing, then I choose this. Okay, but B has not made a choice already. And if you include that point in the discussion, then it is possible that your answer could be different. Okay, and this is what I'm writing here. It says maybe the rational agent should realize that it is better for both to stay silent. It's not a very deep statement, but somehow it requires a lot of convincing to people who have been exposed to game theory before. Okay, so when this obvious point was made in academic settings of game theory discussions, then people, of course, you know, these are smart people, so they said that, okay, you are right. So this, if people go beyond this argument, they are super rational, and then they can choose to, both of them, not testify. And this goes beyond rational thinking. But, you know, this doesn't convince me from an outsider's point of view. Why was it rational in the first place? It was not rational. I mean, it is like some people when they apologize but with caveats or something, so that it is not really an apology. So this was some argument was given. We are saying, sorry, this argument in the bracket was given. It was proposed as the best option. For each of them, this is the rational choice. We are saying this is not the rational choice. So you are saying, no, this is a good choice, but it is not rational, it is super rational. Okay? Anyway, you know, that is just fighting about terminology, which we will not do. So anyway, we'll come back to this point again at some point. There is a different game which is introduced later in 1997. It was a model of stock market. In stock market, what people do is they can buy or sell. But if most people are buying, then it is good to sell. If most people are selling, then it is good to buy. So people said that you want to be in the minority. And for this, they made a simple game. Of course, there was some Brian Arthur first, but this game is called Minority Game, 1997. It is defined like this. There are two restaurants in one city. And there are 2m+1 odd number of residents in the city. Each resident every day goes to the restaurant to eat dinner, one of the two restaurants. Okay, and the price of the restaurant is comparable. The food quality is also the same. So there is not much to choose between the two restaurants. The only thing which makes you decide whether which one is better, if it is too crowded, then you don't want to be there. You want to be in the less crowded restaurant. The service is better then. Okay, so the consideration is that you have to decide to go to restaurant A or B, and you would like to go to a restaurant which is less crowded, but you don't know what other people are going to decide. Okay, and your payoff is 1 if you go to a less crowded restaurant, 0 if it is more crowded restaurant. And you are not allowed to talk to other people, you just have to go to the restaurant. Okay, this is the condition of the game. You are not, no communication between different agents is allowed. Okay, so how do I decide? Based on some information. What is the information I have? The information available to all the players is the same information. It is the record of the previous attendances in the restaurant. On Monday, restaurant A had these many people. On Tuesday, he had so many people. On Wednesday, he had so many people, like that. Then you can look at the last 300 days of record or 5 years of record. and see what people choose in general. And then make your choice. So somebody will say that yesterday, A was crowded, so it looks like people are going to A restaurant very often, so I'll go to B. Somebody else will say, oh, but everybody is choosing to go to B, they will flip, and so B will become more crowded, so I will continue to go back to A. Okay, and so different people can make different choices. And another point about this game is there is no strategy using which everybody can ensure that he will win, or even he will win most of the time. The number of people who can win is a little bit less than half at best. Okay, it can never be more than half. Okay, so there is no perfect strategy, but people are still trying to do as well as they can for themselves. They are not bothered about other people. They want to, I want to be in the minority restaurant, I don't care about other people, right? That's the thing. And so what people do is that given the history, they choose some action and they follow it up, and they go every day. Then sometimes they find that their strategy, whatever they picked, somebody will say that on Tuesday I will go to A, on Thursday I will go to B, and so on. And if it works well, then he will stick with the strategy. If it doesn't work, he will change to something else. So it has been studied as a model of learning, adaptation, co-evolution, and self-organization. All these are big words. So learning, of course, you see the data and you have to detect some pattern, that is learning. And adaptation is that depending on that pattern, you have to change your own behavior. And co-evolution is that other people are also changing their behavior. So once they change their behavior, you have to change your behavior again to accommodate their change in behavior. So everybody evolves together. And self-organization is that it turns out that if all these people are learning in this way, the whole system seems to evolve into a state in which large number of people benefit. In the minority restaurant, there are nearly M people, very few, not much less. So, the overall efficiency of the system is high. And, that is why the model became interesting to study. So, I will consider a slight variation of the standard minority game. Okay. So, here, all agents are rational and selfish, and they try to maximize their expected personal discounted payoff. Okay, sorry, 4 words. So it says that I don't want to maximize my win tomorrow, but over next few days. Okay, and only about myself, I don't care about other people, that is personal. And discounted means that winning tomorrow is more important than winning after a year. So you give better weightage to winning in near future than to far away future. And so you make a weighted sum. Wn is the winning on the next day. The angular brackets indicate average value, expected value. And then lambda is less than 1, and there is a weight factor to n, and you sum them up. Okay, so you would like to maximize this W. That is what everybody wants to do. Okay. So if an agent is in a restaurant where there are M plus R agents today, right now we will take a very simple strategy. That what he does, he chooses a real number FR between 0 and 1. Then he chooses a random number and looks at the output. If the number is less than FR, then he changes restaurant. If it is more than FR, he stays in the same. This is called a stochastic strategy. He doesn't have a fixed rule. He has a fixed probability for doing some action. Okay? And so this is what everybody is doing. They are all using stochastic strategy. If you want one particular outcome, you just put FR equal to 1 or 0, right? The strategy, but you are free to choose the value of FR, and different agents can choose different values of FR if they want. Okay? So what choice would you choose for FR? This is the question now, in this restricted setting. In this restricted setting, there is still a problem, which is what I want to highlight. Okay, we are not discussing the most general game. We are discussing this very simple game in which you decide what you do based on last day's attendance record, that I was in a restaurant which was majority. So should I flip or should I not flip, and with what probability? Okay. So the agents, so this guy, he's not very smart. So he says, this is very tough problem. I think I should consult a professor in ICTS or this reputed business school to find the best possible choice of FR. Okay. And in general, we expect FR to be an increasing function of R. Like if you are in a restaurant with lot of people, then you will want to flip with a bigger probability. Okay, so if R is less than 0, if you are in a minority restaurant, then the advice is win, stay, lose, shift. If you are winning, why change? Just stay put. So put FR equal to 0. Okay, and set FR equal to 0 for R negative. You can prove this more precisely with rigorous mathematics, but right now let us make this at this level of plausibility, that if you are in a minority restaurant, I think it's reasonable that you may not want to shift. Okay, if you are in a majority restaurant, but R equal to 1, so the split is M in one and M plus 1 in the other. The payoff of M plus 1 is 0. So you are still losing, but now you have to decide what to do. So the advice for R equal to 1 is also to stay put. It says that, look, we know that these people in the minority restaurant are not moving. They have put their FR equal to 0. Okay. So now if you go there, if you move, you will make that M plus 1 and you will still lose. If you stay here, then it is possible that somebody else in this majority will move there, and then you will become the minority and you will win. So there is no chance of your winning if you move. There is some chance of your winning if you stay. So please stay. So this advice is given to all the agents in the losing group today. And so no one moves. And the situation repeats again the next day. It goes on like this. It's a trapping solution. Okay. So clearly, this is the worst possible strategy. If these people are losing and you say don't move, the advice is stupid. These are my words, and I'm deliberately using unparliamentary language to make a point. So the advice is justified in game theory using complicated arguments similar to that used in prisoner's dilemma. In the prisoner's dilemma, you gave some messy, complicated argument to say that everybody should defect. Here also, they are saying that, people in this minority restaurant, they should stay put. Okay. So in the state M plus 1 split, all agents not moving is a Nash equilibrium. This is technical word for it. And any single agent cannot do better by moving by changing his or her action. Okay, but how to get out of this problem? The resolution is very simple. The resolution is fire the consultant. Okay. So in formal terms, what does fire the consultant means? You have to change it says use a different solution concept. It is a word in game theory which means a solution concept is a meta strategy. It is the strategy to select strategies. So one meta strategy is find the Nash equilibrium and go there. Okay, we are saying that no, that is not a good meta strategy, and you should use a different solution concept from Nash equilibrium. Unfortunately, a huge amount of literature in game theory only deals with Nash equilibrium. And you give a game, the first thing they want to do is to find the Nash equilibrium. So it is known, of course, it is given in textbooks on game theory. Nash equilibrium solution need not be unique or optimal, as is known in the prisoner's dilemma. There is a Nash equilibrium, both people defect, but it is not optimal. The key point to realize here is that the agents are going to decide and other agents are not, strategies are not yet frozen, and this point should be kept in mind and it can change the answer. Okay, so this is just, I copied the top page from this book, General Theory of Equilibrium Selection in Games by Harsanji and Selden, and it says the need for a new solution concept. This, 1 and 1.1 is this purpose of this book is to introduce a new solution concept, something. Okay, so this is just to explain what is the word solution concept. It is well used, and these people are actually Nobel Prize winners. And this book is quite influential also. So it is quite allowed to use different solution concepts. People have used it in the past. We are not being totally off the rocker if we propose a new solution concept. Okay, so we proposed an alternative solution concept called co-action equilibrium. In co-action equilibrium, the agents realize that all rational agents in the majority group are in the same boat and they will choose the same F0. Okay, F0 is the thing, their shift probability. If you use this assumption that they will choose the same value of F0 and again do the simple expected calculation, you find that the F0 is not 0. Optimal value of F0 is not 0, and so you avoid the trapping state. With some probability, people will shift. And this solution concept avoids the trapping state. Okay, so I have 7-8 minutes. So let me just discuss one more game. It's called the Samaritan's Curse by Kaushik Basu. He invented this game, 2019. Kaushik Basu was a financial advisor to Manmohan Singh when he was the finance minister. So this game was designed to illustrate the point that sometimes it may happen that agents want to help a third party. So Samaritans are people who help others. And so this agent wants to help others and takes action for this. Another agent also thinks similarly and acts in the same way. So individually their action would result in a favorable outcome, but both acting together without consulting each other could end up choosing an action that leaves the third party worse off than they were before. So it happens often in politics. You want to do something with good intentions, but the actual effect of your actions is bad. And Kaushik Basu is trying to illustrate this issue or problem with this particular game. And so the game is like this. There are two industrialists. They have some action they have to do, like set up a factory in A or B. And another industrialist also has a similar action, A or B. And their payoff are like this, some numbers. But now the effect of their actions is also felt on other people who are like the poor people who are not part of the decision making. So they have a payoff. If these people choose A and A, this guy is the third party, which is sort of representative of the poor people, will get a payoff 2. If they choose this one, he'll get 8 or some such thing. Okay, so this is a payoff matrix for agents. The agents know that this is their, both of them know this fact. This is the standard setting of game theory. The payoff matrix is known, and they choose the best strategy. And this is the Nash equilibrium. And in this case, the bystanders gets 4 units. Okay, this action affects the poorer people. These people are not part of decision making, but have to bear the, this we have just said. So the rich industrialists now, they go to a consciousness raising weekend meeting in a seminary. Seminary are these Christian missionary schools where people train for religious education. And they are made to realize, they give a lot of seminars and they are made to realize not to be so selfish and they should worry about others also. Okay, so these people are convinced of this fact that they should worry about others. And so they said, each person now constructs a new payoff matrix in which the entries are the sum of his own payoff and that of the bystander. So he says, I will not only maximize my own profit, I will maximize my profit plus that of the bystander. So he is part of me, I will think of us together. And so they make a new matrix which looks like this. You can just see that those numbers are there. And now they optimize over this new matrix. and the Nash equilibrium corresponds to this highlighted entry. And in this case, the bystander gets 2 units instead of 4 before. So both of these people are trying to do good for the bystander, but is actually end up getting worse. Okay, so that is the game. The details of the payoff are not important. The key idea you should be able to follow. So what is going on? That sounds like a paradox. I'm trying to do good. And the resolution of the paradox here is that one should realize that payoff of the bystander depends on the action of other agents, not just mine, but what the other guy is doing. I should have realized this. When I did the calculation, I just took my profit plus that of the bystander and maximized it. I didn't worry about that this outcome will depend on what other guy does. And secondly, it shows that Nash equilibrium is not necessarily an optimal outcome. I wanted something for the poor, then I should do something, not blindly use the payoff matrix to choose my action. Okay, the error was, the aim was good, but the execution rule was bad, and the execution rule is what we call solution concept. Okay, so concluding remarks. One should be careful in applying game theory considerations to real world applications. Like, when people are choosing mates or they are choosing shirts, consumer behavior you are trying to model. It's not very easy to model it using game theory considerations because, it's the first line doesn't, that thick book on game theory doesn't get off the ground. I try to read the first thing. You have to optimize a real number and I'm not getting it. I don't know which real number to optimize. This is not to say that one should not think logically, but aware that the answer depends on the implicit assumptions made in the analysis. So if there is a mistake, don't blame it on mathematics. It is not the fault of the inequalities in arithmetic that you got the wrong answer. There was some logical error in assumptions which are somewhat hidden and they are ignored. And so these are called implicit assumptions made in the analysis. One may need to go beyond Nash equilibrium considerations to get a desirable solution. A new concept, we have introduced a new concept called coaction equilibrium. It is just a spiel because we wrote it. And let me warn you, we wrote this paper some time ago and it was just lost. No economist bothered about it. Okay, but I think it's a good idea, and maybe give a little bit of publicity, and maybe it will work better. And anyway, the last comment is that game theory should not be treated as a device to legitimize greed. I didn't discuss all these issues before, but what happens is that I have some aim to do, and then I cook up some funny looking mathematics, and then sell my idea to other people by saying that, but the game theory tells me that this is what I should do. And it's sort of, people are scared of mathematics and they take it as nothing can be done now, mathematics has said that you should do this. It's not true. What the mathematics says depends on what you put into the payoff matrix, what you put in the solution concepts, and all these things should be kept in mind. So that is where I should stop, and I'm happy to give answer some questions if any. There is a list of references which you can consult if you want to discuss them in some more detail. It's not exhaustive, of course, but actually, if you say game theory in Google, you will get nice textbooks. These are the less accessible papers which I listed here. Okay, so I'll stop here.
Thank you very much. So before we take questions, I would just like, as is traditional, to give a small memento, which is the ICTS mug and the hoodie.
Thank you. Thank you.
For this thing. I would also like to, at this stage, give a small memento to our chief guests of honor. It is a small Buddha statue.
Nice.
So I would like to present to both of you this thing. You can take a look.
Nice.
It's a sandalwood.
Can you show this to
thing.
everybody?
Yes, we'll. To commemorate the event and the occasion. So thank you, everyone. And now we can have some questions. Please wait for the microphone to come near you. Please raise your hands. Herbert?
Since you mentioned the Nash equilibrium many times, I mean, is there general methods to actually compute the Nash equilibrium?
So, yeah, so what people say is that Nash equilibrium is the sort of stable solution against one single perturbation. So, if other agents are frozen and you make 1% change their opinion, that cannot do better. This is true for all single moves, but correlated moves with two or more are not part of the, then Nash equilibrium is not there. In spin classes, you will say that if there is some sort of state, it is not the ground state, but it is single spin flip stable states. That's all it is. And in that context, it doesn't sound so.
Is there any T?
There is no aura attached to Nash
T is there, no?
equilibrium.
Okay, Alana. Abhishek.
I was just thinking, like, for example, in traffic, there also it's a similar issue, right? Because everyone is trying to optimize, like, they want to reach fastest, right? But in the end, this creates a huge jam.
Traffic jam.
So is it a similar thing, like, because one is not trying to evolve a global strategy, but just a very local, maximizing, like, my own gain. I'm trying to shorten the time I would take to cross some signal, right? But I'm not taking the global. I'm trying to do a global optimization.
Yes.
So it must be a similar problem.
Right? Yeah. So all these problems are, once you pose them suitably, they can be addressed using game theory, and the answers may not be always useful.
But it seems like an obvious thing, right? I mean,
no. So a lot of these games are called congestion games, and traffic is part of these congestion games, and there is fairly well developed treatment of these. No, so the obvious strategies are, of course, there. Like if you have an empty stretch, go a little bit faster. Nobody doubts this part. But suppose you have two different options. Go by this road or this road. This road is a freeway, but it has heavy traffic. This road is less traveled and, not much traffic, but it is not as fast. But, if that one is overcrowded, then you will actually, Google will suggest that you take a diversion, right? So these kinds of diversions can be suggested by Google based on such game theory considerations or optimization considerations. It becomes much harder if everybody is trying to optimize in the same way and so on and so forth.
But this is where maybe, I mean, as you said, it's mostly individuals trying to maximize, whether there is a scope for individuals also paying attention to the cooperativeness. That is probably more difficult to kind of include in the considerations as it's normally framed, I guess.
So let me just say that in this third one of these, it's the same minority game, but we said the agents try to maximize their long-term winning, not over one day, but over 1 year or 2 years, in which case there is sort of a bound that you cannot do better than m over 2m plus 1. But can you get there? Can you get m over 2m plus 1? And the answer is yes. They can do this if they form some kind of a cyclic state in which out of 2m plus 1 days, everybody gets to win m times. Okay? But this was the hard point. The hard point is that the agents are rational. They want to optimize their long-time gain. And so they will agree to coordinate with each other and form a cyclic state. This was not easy to accept And we had a lot of trouble in getting this paper accepted by standard econophysics journal. They said, but you know, that is, so the game is a game in which people are competing against each other, but the best they can do if they all cooperate with each other together, just like in prisoner's dilemma. Okay, so but that is against the grain of the individual deciding and something, so you know, it doesn't seem to go well with hard-boiled game theories.
Yeah.
So I was thinking in terms like in opposite terms in case of mechanism design, how can an adversary convince the rational agents that other agent is not trying to harm you and maybe there can be a cooperative non-Nash equilibrium solution? So as an adversary, how do you encode it into the system of mechanism so that the game...
Adversary? I'm not an adversary, I'm an outside consultant. The game theorist is not really one of the people playing games. He tells the agent, you should do this, you should do this. No, if I'm an agent, you know, why call me an adversary? The starting point in game theory is that agents are selfish. If you want the agent to do, you know, this person says the best for this and that person says the best for this, you can just exchange the names. Okay? But the idea was that there are different agents and they have optimization goals, but these goals are not compatible with each other. Then how do you make decisions? That's the general problem, and all these things are special cases of that general issue. So for example, people have said in this prisoner's dilemma, these are very wise people long ago. So they said that I don't believe in all these game theory. I'm a religious person. And God has told me that I should not testify against my friend. Okay? And then I will follow this advice irrespective of what he does. So they say that this is the Christian ethics and I should use the Christian ethics to decide what I'm doing. But you know, okay, that's an allowed possible choice, but this is a model problem. If you are going to assign the decision-making rule to some third party called God, then the game theory has nothing to say in this matter. Okay, so just a minute. And since this question came up, I was just thinking that, but in Christianity, you know, people like to confess is better. You have done some crime, you better confess. So both of them confessing is actually perhaps the Christian thing to do. But that's sort of just names of things, no? It doesn't address the origin. Okay, so let me not more.
Yeah, so if you're not going to involve a third party in this decision and you keep the game the same, then like if somehow you manage to say like two people manage to have some trust in them, why does it make sense for like one of the parties to still say that, okay, the other person is going to cooperate, but that just means that...
Okay, so actually, when I first read this Samaritan game, I thought it was very contrived problem and not very convincing. Okay, but you don't have to quibble about the details of the payoff matrix. That is not the point. The point is that there are these two agents and they are trying to individually try to optimize something and they don't manage to do it. Okay, which is the same as in the prisoner's dilemma. You know, each of them tries to, some argument or the other they use. I would say that if you were really trying to help the poor, he can take his 100 units of profit and give 8 units to the poor, not directly. Why do you have to go and optimize your payoff matrix with the addition of sums or something, right? So that's not the point. The point was that it is possible in some settings that you try something and the outcome is not good. But that is because you didn't actually envision the possibility that your way of optimizing was not ensuring the outcome that you want, which is the whole point. The whole point is I'm trying to optimize using some payoff matrix and local optimization, but it's not giving me the answer I would have liked. So I should fire the consultant was the idea.
I think the problem is the fact that individuals can make their own decisions, and the prisoner's dilemma exactly points out this fact that given that if you manage to somehow convince the other person to cooperate, it's in your best interest to not cooperate.
Yeah, no, so
So
the
then
point
why
is,
would you
in the
end up-
setting of the prisoner's dilemma, communication between the agents is not possible. You cannot convince him of anything. If you change the setting, then it is not this game, it is some other game.
No, but okay.
Hmm?
It's just like in each case, whether the person, other person is cooperating or not, it's just best for you to not cooperate, right?
Okay, no, very good. So you are actually repeating what a lot of people have said before. And let me just say that once in US, they actually had a virtual meeting of 100 game theorists. All of them were described this problem in some detail, and they were told, what will you do given this setting? And everybody knows what is the outcome, and it is not very good. And 70% of them will say that if I am one of the prisoners, I will defect. They will choose the strategy to defect, independent of all the arguments other people gave about the usefulness of cooperation and so on. So this brainwashing goes quite deep, and a lot of people are not convinced of the correctness of the alternate. But I thought, can I? So this bottom line, there were 4 choices, 4 possible games, and people chose this one, and it is clearly not the optimal choice. So whatever mumbo jumbo argument I used to determine this one is a suspect argument. I don't want to keep on repeating it. You can keep on repeating that argument ad nauseum, and you will get the same answer if this is the best choice, and it's not. End of discussion.
No, but I think the problem is greater. For example, like this is also the argument that people use for, say, this strategy of mutually assured destruction and proliferation, nuclear proliferation sense. The point is that, like, if there are 2 warring nations who decide that they will choose to give up their weapons, and can you really trust the other nation to actually give up theirs? And if they fail to do so, it's just worse for you. And if you keep your weapons, it's just better for you. So,
okay. So I will
why
say
would
that
either of the
it will be very hard
nations-
for me to convince you in a few minutes about this. We can discuss it privately later.
Yeah, I think it's okay. Abhinav.
So in settings like machine learning and even simple settings like linear regression, there is a notion of regularization where you sort of try to bound the coefficients that show up in your estimation, and that helps your model this notion of regularization. And I was wondering if there's a notion of regularization which would go between a cooperative game and a non-cooperative game. Can you somehow translate your
Yeah. So in this particular stuff, we started with a non-cooperative game, but then it's turned out that in the end, if you really want best long-term personal benefit, then you should cooperate with others in this particular sense. Okay, there is a particular sense in which you should cooperate, not in just abstractly. So it's possible. One part of this machine learning is just parameter estimation. There is some data, it's huge amount. I want to compress it into 1 or 2 numbers. Okay, so you do the data compression. Then what do you use those 2 numbers for? Or how do you use them? That is the question. That the data analysis, data compression will not tell you. That you have to decide in addition. And that is the second part we are discussing here really.
Last question, maybe.
So it came to my mind that in many situations in real life, the rules of the game itself might be a parameter that can change. And in real life, I mean, like you could elect new people who would change the rules of the game, for example. Or if you're trying to bring about behavior change, you might want to change the game. Like say you want to change the way people drive, you might change the traffic patterns in some way. So are there frameworks to study optimal solutions where you can vary the rules of the game in some framework and also vary the strategy?
I guess they are there, but they are not usually studied in the name called game theory. Game theory sort of starts with the definition of the game. You are free to define your game, but once you define it one way, then stay within that parameters and try to see what we can do within this game. If you want to change the game, it's okay, go ahead, change it.
It's a limitation of the framework, I guess, that it has to be rigidly...
No, so you can say that, okay, I'm a casino owner. Which game should I install in my casino? In itself, this will not be answerable in game theory. If you say that, okay, this one will give me this much payoff, this one is, or that kind of stuff, then I can address it. But selecting between different games, which game should I select, is not an option. You can have a super game in which you can say, in the beginning, I will take the VRS1 or VRS2 scheme and so on. Then it is still a game and then it works within this framework. But I don't know of too much of actual work in this kind of setting.
And I guess the problem would be that in some of these games, the agents can affect the rules of the games themselves, right?
No. So you can have very complicated situations. They are very hard to study in a general setting. And if it is too specific a setting, then it is not interesting enough.
Okay, thanks for the nice discussions. So let's thank Deepak again for a very stimulating talk. And once again, I would like to thank our chief guest for traveling from Chennai all the way to be with us for today. And I invite you all for the tea outside. So please join us and thank you.